So this is lesson 3, naming and writing formulas. Our objectives are to learn how to write formulas and name compounds and learn how to assign oxidation numbers. So we're picking up on page 10 in your notes, and we're going to start with naming and writing chemical formulas. So each element within a compound has its own charge. We call these charges oxidation numbers. When you add them all up within a compound, they will equal 0. Oxidation numbers can always be found on your periodic table, and they are the only numbers that we really haven't used yet for anything, and they are those plus and minus numbers that you see at the upper right hand corner of the chemical symbol itself. So what I wanted to add to this is that because the oxidation numbers add up to 0, that shows a conservation of charge. So as oxidation numbers exist because different compounds or different atoms can take on different charges in different compounds depending on what elements you are bonding. And the number of electrons those elements will either donate and give a positive charge or accept to become a negatively charged ion or to become negative charge. So if we look here at a little bit of an example, sodium is a +1, fluorine has a -1 oxidation number. So this will give up 1 electron to the fluorine, fluorine gains it, and therefore will form NaF, which is sodium fluoride, and we're going to talk about how we name that compound in a second. Calcium is a +2, chlorine is a -1. So in order to balance this out, we're going to have to give a symbol, a subscript, to represent how many atoms we need of that particular element to balance out the charge. So calcium is a +2, chlorine is a -1. In order for these numbers to add up to 0, we're going to need 2 chlorines to give us a -2. So when we give the chlorine a subscript here, that tells us we have 2 chlorine atoms bonded with 1 calcium atom to become a neutral compound and form calcium chloride, CaCl2. So the rules for assigning oxidation numbers are as follows. Uncombined elements, meaning not paired up with anything else. Uncombined elements not bonded to any other type of element have an oxidation number of 0. They're automatically neutral. This includes any formula that has only 1 chemical symbol in it, single elements, and diatomic elements. Remember, the diatomic elements are Brinkelhoff, okay? Those are the diatomic elements and any single element. So these are all going to have an oxidation number of 0, as well as any element by itself. So here are some examples. Let's say you have carbon. It's going to have an oxidation number of 0. Nitrogen, oxidation number of 0. Bromine, oxidation number of 0. Iodine, oxidation number of 0. And we'll put the assigned oxidation numbers up in the right-hand corner when they're not bonded with anything. So when we are talking about compounds, we have to look at their charges in the upper right-hand corner of the reference table. So in compounds, remember, they are neutral and have a 2 or more different elements bonded together. The sum of the charges must add up to 0. So the ions within a compound have oxidation numbers equal to their oxidation number found on the periodic table. So here's an example. We have sodium. There's one of those with a 1+ charge, so that gives you a +1. You have 1 chlorine, so 1 times the -1 charge that it takes. And when you add these up, you get 0. Another example here, magnesium nitride. So magnesium has a +2 charge according to the reference table. So we have 3 of those. The subscript tells you how many atoms you have. So 3 times 2 is a +6. And then nitrogen, there's 2 of these. So we have the 2 here, times the charge that it takes, which is a -3. So this is equal to -6. And when you have 6 minus 6, you end up with 0. The next example we have is HNO3. So for hydrogen nitrate, we can call it, we have H, we have to look at nitrogen, and we have to look at oxygen. There's 1 hydrogen times a +1 charge that it takes, gives us a total of a +1. Nitrogen, there's 1 of those with a charge of +5, will give us a +5 overall charge, and then 3 oxygens times the charge on the oxygen. Oxygen is always going to be -2, always. So we're going to do 3 times -2 is a -6, and when we add all of these up, so you have 1 plus 5 is 6 minus 6, and that gives us a neutral charge. So the oxidation number is the number inside the parentheses. It is the charge on just 1 atom of that element. Remember that we almost always write the positive element first and the negative element last in a compound formula. So the first one that is always written will always be the positively charged ion. So in this case, it's always going to be a metal written first, then the non-metal. Or you can have a positive polyatomic ion, and I'm just going to abbreviate it, plus a negatively charged polyatomic ion, which there are if you look at table E. Okay, so here are some examples of what I was talking about here. Here is hydrochloric acid. Exception to this rule is ammonia, which is NH3, wherein you have your negative charge written before your positive. Okay, and here's your positive and your negative here. But this is actually negative and a positive. This is because of the hydronium ion here, the H3. Okay? And what actually happens is when you have H3, it then will turn into a negative charge because you have too many charges here. All right, so moving on, we're going to look at group 1 metals. They always have an oxidation number of +1 when in a compound and bonded to other species. Group 2 metals always therefore have an oxidation number of a +2, and also when they are located within a compound. So here is an example. Sodium is a group 1 metal, +1, bonds with something that is a -1. Now calcium being a +2 and chlorine, 1 atom is a -1. We need 2 chlorines to balance that out. So this has an overall charge of -2, but the chlorine itself only has a -1 charge. When we add them up, though, it comes to 0. Fluorine is always a -1 or a -1 in compounds. The other halogens, however, in group 17, chlorine, bromine, are also going to be -1 as long as they are the most electronegative element in the compound. What does this mean? This means that we have to make sure that we look at their electronegativity values before we can determine the charge. So here is an example. You have sodium fluoride, hydrogen bromide, and lithium chloride. These are all examples of the charges that they take in this in these bonds. So sodium is a +1, fluorine is going to be a -1 here, hydrogen's a +1, bromine -1, lithium +1, chlorine -1. Hydrogen is a +1 in compounds unless it is combined with a metal and is at the end of the formula. Then it is a -1. Okay, so if we look here, hydrochloric acid here is going to be a +1 and a -1. Here is a +1 and a -1. If it's at the end of the formula, it's going to be a -1. Oxygen is usually a -2. Hydrogen, +1. Oxygen, -2. Okay, there's 2 hydrogens, so that will give us a +2. A -2 equals 0. Carbon will be a +2 in this case. No, +4. I'm sorry. Let's erase that. So this has to be a +4 because oxygen is a -2 and there's 2 of those. So to balance that out, it's a +4 there. So when they actually are combined with fluorine, which is more electronegative, then oxygen is going to become a +2. That's the only case. So we have to know this. When combined with fluorine, then oxygen is a +2. So here's your example. +2 here. Fluorine is a -1, but there's 2 of those, so that will make it a balance of charges here. 2 times -1 is -2, +2, and then that balances. So that's how we determine the neutrality of a compound. So when in peroxide, okay, and this is peroxide, H2O2, or anytime you see an O2 at the end, when in peroxide, oxygen is going to be a -1. So peroxide is a compound that has a formula of X2O2, and X obviously is not an element, and X is any metal or non-metal that can bond. With a plus charge. Okay, so what this means is that it could be a non-metal as long as it could take a positive oxidation number, because it has to be written first. Remember, the positive goes first, then the negative. So here hydrogen is going to have a +1 charge. Sodium has a +1 because it's a group 1 metal. And with the +1, let's make this look nicer here, +1, there's 2 of those. And the O2 here is going to be a -1 because there's 2 of those. And also in sodium, so this is sodium peroxide, not hydrogen peroxide, but sodium peroxide. You have sodium, 2 of those with a +1 charge, adds up to a +1. And then since oxygen will get a -1 here, according to the rule, then 2 of those would be a -2. So the sum of the oxidation numbers is in polyatomic ions must equal the charge on the ion. And we could see table E in your reference tables. Again, guys, last lesson, my values for electronegativity were a little different. That's because I had them memorized from the 2008 edition, and it did change in 2011. So, but the electronegativity differences were the same. So just to let you know. So there might be some slight differences between my values if I'm still using 2008. So here we have chromate, and you have Cr2O7. There's 2 chromiums and 7 oxygens, and then we find their charges. So 2 times a +6 is a +12, and you have 7 times a -2 gives you a -14, which then gives you an overall charge of -2. So this has to be an ion, or the polyatomic ion chromate, so it's going to have an overall charge of -2, and that will be given to you in table E, so you don't always have to memorize that. But polyatomic ions are their own entities, so we can put parentheses around them to indicate that it is a polyatomic ion. So this ion here would have to be, would bond with a +2 metal, or any other element with 2 of them, okay, or any other element that adds up to a +2 to balance out the equation. Okay, so let's note one thing here. So compounds containing polyatomic ions have both, and we talked about this before, ionic and covalent bonds. The ionic bond is occurring between the positive polyatomic ion and the negative metal, or a positive polyatomic ion and a negative polyatomic ion. So let's look at this. We're going to practice a little bit. So it says identify and list the polyatomic ions in the following compounds using table E. The first one we will do together as an example. So you have 3 of the NH4 ions, and when we look up the charge, it's a +1. I'll put a +1 or a plus, okay? And we have the phosphate ion, PO4, which tells us there's only one of those, and it has a -3 charge. So let's look at, to make sure that it balances out. 3 times a +1, right, equals a +3. And then you have 1 phosphate ion with a -3 charge equals a -3. So therefore you have 0. So this compound does exist. You have sodium bicarbonate here, okay? And what we have to do is we have to look up our possible polyatomic ions. So on table E, I see that HCO3 is a polyatomic ion. So I have sodium, and there's one of those with a +1 charge. And I see that HCO3 has a -1 charge, and there's only one of those. So +1 times 1 equals +1. And then there's one of the bicarbonates with a -1, and then that will equal 0. All right, ammonium nitrate. Oh, so I see that there's more than 2 elements. I actually see 4. So there's a possibility that there's 2 polyatomic ions here. So if I look at table E, I will see that NH4, the ammonium ion, is there, as well as the NO3 ion, the nitrate ion. So if I look at their charges, NH4 is a +1, NO3 has a -1. If I add those up, they both equal to 0, and therefore I have a neutral compound. H2SO4, this is sulfuric acid. Now we have to look at our exceptions, our rules, okay? And I see that SO4 on my table E is the sulfate ion, which has a charge of a -2, or a 2-. Doesn't matter how you write it. Okay, so let's say this is 2-. There are 2 hydrogens, so we have 2 hydrogens with a +1 charge. According to the rule, it's going to take a +1 with a polyatomic ion. So if I have 2 hydrogens with a +1, I have an overall of +2. Then I have 1 sulfate with a -2. Gives me a -2. Add that up, 0. We're good. And then we have potassium nitrate. So potassium by itself has a +1. NO3, again, we know that this is a polyatomic ion, this one is a polyatomic ion. NO3 has a charge of -1, so we add those up, equals to 0. Right, so let's look at this example. Hydroxide, the hydroxide ion. Oxidation number of oxygen is always going to be a -2, except in peroxides. Therefore, hydrogen has to have a charge of a +1, and it's backwards here, it's written backwards here, but this is a polyatomic ion, so we have to make sure that the rules are being followed. So we have to note that they have to add up to -1 because that's the charge on the ion itself. Okay, so -2 here and a +1 gives you an overall charge of right here, a -1 equals a -1. So that's where the polyatomic ions get their charge. They're not compounds. Okay, so they have charges because they are ions. Another example, the phosphate ion has an overall charge of a 3- or a -3. So the oxidation number of oxygen is -2. There's 4 of those times -2 is a -8 total on the oxygen. Then phosphorus has an oxidation number of +5. And then we have to say to ourselves, is this one of the choices on the table? Let's look. So since this is one of the choices, this is a possibility, and this is how we figure out which oxidation number to assign when it doesn't fall under the first choice. Okay, so when we add this up, we have -8 plus 5. That gives us a total of -3. That's where that comes from. Okay, finally, last but not least, some more practice. So to determine the oxidation number of each atom or polyatomic ion in the compounds below, hydrogen is going to be a +1, oxygen is a -2, calcium, okay, and then oxygen, we're going to just split it up here to help us. Sodium is by itself, then we have iron, chlorine, so we're not actually looking at each, the total. Okay, we just want to assign an oxidation number for each atom or polyatomic ion by themselves. So here we have hydrogen and oxygen. So calcium is always going to be a +2, therefore oxygen has to be a -2 here. Sodium, it's by itself, so it has a oxidation number or an oxidation number of 0. Iron, okay, so iron can have two different charges here, a +2 or a +3. While chlorine, we know, is always going to be a -1, and we have 3 of those. So in order to balance this out, iron has to be a +3 to get a neutral compound. So if we put iron +3 here, then you have 3 chlorines times a -1, that is going to equal 0. So you can double check yourself. Hydrogen, or peroxide, is now our exception, right? Peroxides, oxygen's not always going to be a -2. Hydrogen is a +2, or I'm sorry, a +1, right? So let me erase that here. Okay, +1. And then oxygen is going to be a -1. So we have 2 hydrogens and 2 oxygens to balance out and give us a total of 0. Lithium hydroxide, lithium or lithium hydride, lithium by itself, group 1 metal, is always going to be a +1. And in this case, hydrogen, it's at the end of the compound, is going to be -1. And then we have hydrosulfuric acid, okay, or we can call it sulfuric acid. So let's break this up. SO3 is a polyatomic ion that we can find on table E. Okay, so hydrogen is going to be a +1. And then the sulfate ion, there's only one of those, which, I apologize guys for that. Anyway, yeah, so the SO3 has a -2 charge. And there's only one of those, so that will balance out because there's 2 of these times 2. Okay, so 2 minus 2 equals 0. Another way, if we need to know what every single component is, okay, we know that the SO3 ion has a total of a -2. So let's break this up. Oxygen is going to be a -2. And there are 3 of those, so that gives us a total, 3 times that will give us a total of a -6. And then sulfur, there's only one of those, and sulfur has a +4. Okay, so 4 minus 6 gives you the -2 here. So we're going to say that sulfur has a +4, oxygen is a -2, hydrogen total +1. So we broke it up. We broke the polyatomic ion up there. And that concludes lesson 3.